All right, hi everyone. Continuing with our topic 7, hearing and noise. Welcome to subtopic 7.3. So this one I'm going to talk about sound perception. The key word perception is, this is the experience of hearing. Okay, so if I say I heard something, that means I perceived that auditory signal, as opposed to I sensed it. Sensing is activation of our neural receptors. Perception is the cognitive, is the mental experience from those physical energies. So we're going to get to that point here. So we make a big distinction right off the bat that everything we've talked about so far are about the physical properties of sound. The physical energies can be objectively measured with these tools, meters that we have. Loudness, on the other hand, is something that's only experienced inside the head. So how loud is something is not something that can be measured with an external device. How loud something is loudness only exists in my perception, in my experience. So it's a subjective measure. We can ask people, hey, how loud do you think that was on a scale of 1 to 10? But we can't put a sensor on the human's ear and detect, oh, this is how loud that was. We can detect the sound pressure levels, but we can't detect loudness. That's a psychological concept. All right, so changes in sound pressure level do not equate to the same changes in loudness. Now, sound pressure level changes, yes, the loudness does change, but not in a easily definable way. Okay, it's certainly not linear, certainly it's more of a stepwise, dependent on several other factors. So yes, it depends on the pitch and the frequencies. We did the example. I've had to take my soundboard out for now, my synthesizer, but the 4,000 hertz sweet spot, that is the most sensitive frequency for human hearing. So loudness depends on the pitch as well as the amplitude, so to speak, of the sound pressure level. Also, the changes depend on the absolute values. So we can notice if something changes from 1 decibel to 2 decibels, or from 5 decibels to 15 decibels pretty easily. But that same magnitude of shift depends on where you're starting from in terms of how it's experienced. Okay, so loudness is a psychological dimension, but we can still measure it. So we can subjectively ask people, hey, how loud do you think this is? And how much louder do you think this is? And we can get quantitative answers. The units for this psychological dimension are called sones, S-O-N-E, okay? That's one sone is equivalent, and this is, again, we're defining it somewhere, but the experience of a 1,000 hertz tone played at 40 decibels of sound pressure level, that is the equivalent of 1 sone. How loud that sounds? 1 sone. Now, I can change the pitch, I can change the volume, the intensity, I can change a number of things about the sound. If it sounds to me inside my head like it's twice as loud, then the unit is 2 sones. Okay, so I don't know how I got to twice as loud. I could have changed the sound pressure level or the pitch or both. But for whatever reason, inside my brain, that seems like it's twice as loud. So this doesn't keep, doubling like this in a nice linear fashion. It actually shows this sort of a pattern. But as a rough approximation, we're usually not dealing with things that are considerably higher than a couple of sones for the most part. And things get, a rough approximation here is if you add 10 decibels of SPL, you're roughly doubling the experienced loudness. And especially at these lower ends here. So it's kind of similar to with low frequency, how we have a lot of change in the expression of the signal that could be due, to either changes in the sound pressure level or the frequency at that certain, that top corner of the audible frequency spectrum. So anyway, just rule of thumb here, note that if a sound pressure level doubles in intensity, it's a 6 decibels. But loudness, it's 10 decibels roughly, again, according to certain parts of this curve. So again, that's one difference between the changes in the physical world where I can measure decibels of sound pressure level, and the psychological world where I experience loudness only in my head. Okay, so again, as we mentioned, we can change the pitch or the sound pressure level, and this will have potentially impacts on our experience of loudness. And this is kind of what I was trying to explain in the previous slide. There are regions here where it can fairly dramatically change with a little bit of a change in frequency or a little bit of a change in sound pressure level. Now, the way this breaks down is we can have these sorts of what we call isometric or iso loudness curves. So what you see with each of these contours here is basically, now these numbers, these aren't, wait, is this zones? It is zones. These are zones. Okay, so each of these curves represents, no, I'm wrong, because this is one zone right here, is 40 decibels of sound pressure level and 1,000 hertz. So these are just numbers meant to say these are equal loudness and however that's specified. But basically what this shows is if I want to sound equivalently loud and I'm changing from 1,000 hertz signal to, let's say, 100 hertz, which is here, 0.1 kilohertz, in order for it to sound just as loud, let me get my note. If I move from here, I'm right here, and it feels like 40 loudness, or it's one zone, but let's just say 40 for now. And if I want it to sound just as loud at 100 hertz as I do at as 1,000 hertz, I need that 100 hertz signal to be about 10 decibels louder, about 10, right? So about 10 decibels, I should say, not louder, 10 decibels in greater, 10 more decibels of sound pressure level, right? All right, so each of these curves represents equivalent loudness. Obviously, the sound will change, but my psychological experience of loudness is constant along each of those curves. Okay, erase it. Okay, good news. I set my keyboard back up. So I wanted to be able to show you these pitches so you have a little bit more of a sense for what we're talking about. Okay, so equal loudness curves, and then note the two that we're really interested in. Here's our closest we can get to 1,000 hertz. Now, I can't specify 40 decibels. That's going to be completely, actually, I can't do that anyway because it's a ratio, right? But 40 decibels above the reference pressure, that's all dependent on how you're hearing this. But here is close to 1,000 hertz. I think that's coming through. I think I saw the thing flash. All right, so you know what that's like. What this means is basically I want to sound equally loud. If I were to change that pitch, I'd follow these iso loudness curves to determine what my new coordinates would need to be. And also I wanted to point out one more time our sweet spot, very close to 4,000 hertz, and the closest pitch I could find is this, the B7. So again, that's, we talked about that the other lecture as well, but just to kind of give you that perspective again, so you know what we're talking about. Okay, now our ability to resolve these two dimensions that exist in our heads, loudness and essentially the pitch, we have some capability to differentiate them. That's worth noting. So roughly between 0 and 100 decibels of sound pressure level, we could tell that, hey, that pressure has changed. It feels louder to me. Between roughly 0 and 100. If it's much better higher than that, I guess, or lower, we basically don't have much to say about how much louder, or not accurately anyway. So the key metric usually when you talk about these, how sensitive are people in certain dimensions, is you measure this JND, the just noticeable difference. If I had my sound here, just noticeable difference. Now the ability to tell that that sounded slightly less, like 1 decibel less than that level of distinction is really critical, as it's one of the clues for how we locate the origin of a sound, or we localize a sound. Where did that sound come from? You know, the process by which our perceptual system helps us figure that out. All right. For pitches, our just noticeable differences actually depend very much on your starting frequency. So if you change from 500 to 1,000 hertz, you're doubling it. That's a much easier distinction than 5,000 to 5,500 hertz. It is more of a geometric multiplicative sort of series. So remember, when we double the frequency, we're going up in an octave. But so again, people can distinguish these pitches, and right in the sweet spot, right in the middle of the audible range, humans are pretty good for 0.1% differences in pitch, which is important for things like tuning instruments, right? So the ability to do that and to hear subtle changes is that's about the human ability there. Okay, there is a phenomenon. It's not I didn't hear you exactly because you weren't speaking loud enough, or that noise wasn't loud enough to reach my audibility level. But there's obviously also a lot of problems with sounds overlapping each other and making one important message or one auditory signal mask another. Okay, so you can miss things because of the way that these sound pressure waves combine in space. Okay, so we call this masking, and auditory cues mask other cues, especially if those sounds are close. If they sound similar, then the two sounds are more likely to kind of have a similar propagating sound wave pattern, and they're more likely to become muddied or for one to cover the other. If things are about the same frequency, about the same loudness, then in general, lower frequency cues, lower frequency signals mask the higher frequency ones. So something to consider when you have, for example, male and female voices, and male voices are generally have a lower fundamental frequency than females. And so if I have a room, or let's say I have Kyle Field full of men and women of equal representation, and I have everybody yell, those with the lower vocal range are more likely to be heard over the higher vocal range. So there are exceptions, and I'll talk about them shortly. But what's our design standard here? What do we want to think about? If I absolutely need to be sure that this message is heard, I generally want to go 15 decibels above any potential masking signal in order to get it basically to overpower any masking effects. Depends on the pitch, so it may need to be larger, but 15 is the value that you ought to keep in your mind for the purpose of this class. As I mentioned here, we're at Kyle Field and everybody's yelling, and we have equal number of men and women, and assume that all men and women can produce the same level of sound power. That's probably not true, but let's assume they can. That fundamental frequency for women is in general higher than that of men. And so for the same sound power, the loudness of a male voice is going to be greater than a female voice. Sorry, ladies. Well, you have other advantages though. So I mentioned this one year, and I had a really great question from the students and said, well, then why is it when I'm listening to chamber music, like vocal music, choirs, why is it that I hear the women so prominently? And I thought, well, that's actually a really good question. I'm going to look into that, because that sort of contradicts what I just said here. If everybody is projecting at a certain range, with a certain power, and I'm assuming, if anything, men can produce as much or more sound power just due to physical stature, why is it that women's voices are more prominent? So great question. There's a couple of reasons. And actually, I would say melodically, musically, it's because very likely the highest parts in a song are going to be carried by
the parts of the. I hope this has been working the whole time. I just got a microphone warning. the parts of the song that you listen to that stand out are going to be that melody, that top point for a lot of songs anyway. But what I wanted to point out is this italicized part at the same level of loudness. And so loudness, again, being a psychological concept, okay? And I'm not saying at the same level of sound power output, even though I was, if those could be equated, then then we have more to talk about. But realize that the fundamental frequency of a male voice is, of course, lower than the women's. By the way, fundamental frequency, that's like the lowest frequency in a complex bunch of different frequencies overlaid on top of each other. It's what we usually say, like if I'm singing, it's going to be the pitch I'm trying to sing. That's my fundamental frequency. And similar, right? And so for men, that's lower than for women, as just a basic, general biological thing. So why are women heard as louder than men in a lot of cases? Well, here's my example. So this is Barry White, noted bass vocal performer, male, obviously. And this is Celine Dion, noted soprano. I think she's a soprano. She's at least a female singer. And let's say they're both able to, they're both trained singers, and so they can produce 90 sound pressure levels of, 90 decibels of sound power, let's say, from their vocal machines, their lungs and diaphragm and their vocal cords. All right, so we can produce this much power, but if our fundamental frequencies are different, and remember again with our ISO loudness curves, look at the difference here. So Celine, her voice is going to sound almost 10 decibels louder, according to these ISO loudness curves, than Barry White's. So even though we can tell each is, producing at, we can obviously hear both of them, they're both beautiful singers, but the female voice, by nature of being in this higher sort of ISO loudness curve position, is going to sound naturally louder. And in fact, I went ahead and, so we can project it that way. I went ahead and looked up the choir music, the chamber music vocal range for these two parts, and you can see how much they differ there and how much each of these ranges are affected by these ISO loudness curves. All right, good. Good. Okay, so I think I already said this, the fundamental frequency, this is the lowest pitch, but we usually have several harmonic and complexities to the sound propagated when we are speaking. Okay, there's a lot going on, not just a single pure tone. But that fundamental frequency matters because it carries the majority of the energy of that utterance, right? And so the range here of human speech is roughly 85 to 255 hertz. That's actually, if you look at this, this is, it's roughly the range, speaking range is roughly where a bassist would sing, okay? And so, but that's our speaking range generally as humans as a whole. So females can produce, sounds that low, but it's typically when they're in, speaking range. Now, higher harmonics are what create all the interesting aspects of an individual's voice or of the, I don't have the term yet, of an instrument, for example. So I'll get to the term in a second here. But we're generally not talking, in almost anything we hear, it's a fairly complex sound. It is not a pure tone sine wave, right? But we can describe things that way, and we can produce sounds that are pure tone sine waves. So one of the ways to describe the complexity, or really the full spectrum of a complex sound, is with a fast Fourier transform, a Fourier analysis. And so what you're seeing here is this is one waveform contributing here at a certain frequency. That frequency is the x-axis here in the spectrum, and the power, so to speak, or the influence of that sinusoid is the amplitude here. And so if you can represent this, it's a fairly low frequency but fairly high amplitude, and this might be a lower amplitude but a higher frequency. And now if I had a complex sound that combined those two waveforms, and it might mathematically look like this, if I were then to decompose that with a Fourier transform, I would get each of those components would come out of it. And so then, yeah, basically you get more and more complex signals, you get more and more components to the complexity of, you know, of that waveform. All right, so this is why instruments sound different. Why, well, you know, why does so all this, the last few at least, were the same pitch, the same key I was pressing, but distinctly different sounds. So what's different about them? And they are the harmonics that are basically played, you know, alongside on top of generally higher frequency than the fundamental frequency there. So here are just some examples of power spectra you might measure from different sorts of instruments. And each of these I'm just playing the C4. That's so we can get very different sounds, and that the nature of that sound, so sort of the spectrum of complexities, you know, the frequencies involved, this is called the, and get ready to pronounce this, the timbre. Timbre, not timber, timbre, believe me or not, that's how you pronounce it. And so that word means that's the quality of an emitted sound that basically describes the complexities of these harmonic overtones. Okay, well, cool thing is this concept of timbre is also a good way to describe how we create complex speech sounds, okay? So the fundamental frequency of my voice isn't changing that much, but as I change the resonance chamber of my mouth, my nasal cavity, you know, my throat, as I change that resonant area, different types of or different harmonics are going to be emphasized, different frequencies above that fundamental frequency. So ah, e, o, I didn't change my fundamental frequency, but the reason that you hear those as vowel sounds is because of basically the Fourier transform of that complex sound. So I'm going to illustrate this. This is something I do basically whenever I give this lecture, but I haven't done it in a while. And it's something I was trained to do in high school. I actually was selected for this vocal music group where we did this statewide sort of demonstration of some music that involved harmonic singing. And so basically it's like a chant style singing. You have a common fundamental frequency and you manipulate the resonance chamber of your mouth, so we produce these different harmonics. And if you do this in a resonant sort of chamber, like a gymnasium or you know, an orchestra hall, you get some pretty cool sounds that emerge from a bunch of people doing this. All right, so if you're ready, here we go. And I want you to, in particular, listen when I get to the E's. E has a lot of high harmonics, and I hope you can hear them. I hope so. Let's see. All right, here we go. Ooh. All right. I hope that worked. I could hear the harmonics. I hope you could at home. Okay. So right. So that's how we produce basically vowel sounds, complex, you know, sounds coming from our vocal system. Now consonants, how do those work? Those are basically the attack and the decay on each utterance. So the front end of a sound bite and the back end. How quickly I accelerate into that sound pressure wave, that's the attack, and how we end it, that's the decay. So for example, a b or a w, b or a w. I have very similar mouth movements, but one is sharper than the other. I have a more a greater acceleration to the b than I do the w, right? All right. White noise. Okay, just like white light, which is all the light in the visible spectrum, white noise is similarly all the noise in the audible spectrum. And I could, let's see what we can find if we go online really quick. Let's go white noise. And you all know what this sounds, right? I'm sure. I bet we're going to get a commercial. Yeah, sorry. Edit this
At
out.
iHerb, we make and sell the best health and wellness products on the market because we know what's inside every bottle matters.
White noise. Sounds like fuzz, sounds like you turned on the TV or the radio to a non-existent channel. But what you're hearing right now is the combination of all the frequencies in the audible spectrum, typically weighted in such a way that works with human hearing, like decibels of A weighting. And actually, that's not true. With white noise, it's equal across all of them, because pink noise is human adjusted. It's adjusted decibels of A weighting. Okay, sorry, we're not doing that. Give me pink noise, would you? I don't want to buy it. There you go, pink noise, slightly different. And what this is, again, this is human ear. This is human ear corrected for decibels of A, so that we have roughly equal intensity or equal loudness experienced for all of the frequencies in the audible spectrum. So, roughly 100 to roughly whatever, 8,000. I forget what the high end is. Oh, higher than 10,000. 20,000. That's right. 200 to 20,000. 20 to 20,000. That's it. All right, great. So I mentioned this earlier when I talked about your ability for just noticeable differences in loudness and pitch, how that matters for sound localization. So there are actually 3 types of major cues that we use for the information coming into our ears that help us perceive a sound as coming from a certain location. So interaural means between my 2 ears. So between my 2 ears, the time difference, the level difference, and then cues that have to do with the weird shape of my pinnae and my head itself. So first, the interaural time difference. Because we have the speed of sound is finite and we can think faster than it, we can have cases where if the sound comes from, directly to our left or directly to our right, it reaches one ear before it reaches the other ear. And that difference in time is one clue that we use to determine, okay, that sound came from there or there. Also, if it comes to both ears at the same time, we say, okay, that's either, it's either directly in front of us or directly behind us, right? And then everything kind of in between. And so we're pretty good with just the difference in the arrival of the sound to the 2 ears. That's a pretty reasonable cue for us to be able to get roughly in the right vicinity of where that sound came from. So within 1 degree, in fact, that's pretty impressive. Interaural level difference in this one actually matters based on the frequency of the signal, and higher frequency signals have a much greater difference in the level when they reach each ear if they come from different locations. And this is kind of how you illustrate that. So the head blocks some sound. If sound comes from my right side right now, it's going right to my right ear, but to get to my left ear, it's either got to go and be absorbed somewhat by my head, or it's got to be reflected off of the walls or whatever and get to my ear this way. And so it's going to have a degraded, it's going to be degraded somewhat, because as sound pressure travels, it loses energy, right? And so if I have a frequency that is higher, then I have more oscillations of the pressure wave. I'm going to have a greater effect of that muting or that degrading of the sound pressure level when it runs into obstacles. So for higher frequency sounds, they are more affected by obstacles in terms of how it reduces the amount of sound pressure that continues to propagate. Okay, so we see a very similar pattern with these where, hey, if the level is louder here than here and by how much, that's another clue we use for, you know, orienting spatial localization of the sound. And again, higher is better. So this is the example I always like to use is if you've ever gone outside at night and you hear a cricket, and take a minute and think, where is that cricket? And I bet you can get surprisingly close to that actual cricket if you really wanted to find it, even in the dark of night. And part of that is because, I mean, a major reason is because this is a very high-pitched cue that the cricket emits. You know, the right, I think you know what a cricket does. And because of this cue, this sound localization cue, humans are really good at picking up where the origin of this high-pitched sound is. Okay, so I really like the cricket example. Contrast that with a bass sound, a really deep, low sound, like a subwoofer, for example. And, you know, maybe those of you who have, you know, some experience with like audiovisual design, you might know that in a space where you're going to have low frequency sounds, you can put the subwoofer speaker almost anywhere in the room. And it's because with those lower frequency sounds, there's much less of a difference in the experience based on your orientation to that speaker. It's a much bigger effect for the higher frequency sounds. Some of you may know this guy, a noted industrial engineering PhD student, Johnny Manziel. So this is a pretty cool, here, I don't know if I have it. Yeah, I do, good. This is a nice demonstration. You'll notice that Johnny is blindfolded. This is back when he was training for the NFL, but was still at A&M here, so I could, you know, I had a valid reference. He's blindfolded, and what you're gonna see is this player here is going to clap his hands. A clap has a lot of high frequency sound involved in it. And so that high frequency sound is enough for Johnny to localize the source of that sound with blindfolds on, and then nails that butter pass right here. Yeah. So again, blindfolded. Pretty cool, huh? All right. Okay, good. All right. Now, it's not enough if we only have these interaural time differences and interaural level differences to guide us. It's not enough because there's a key dimension that we're not covering here, and that's the Z dimension. I don't know from ILDs and ITDs if that's the only input I'm getting. I don't know if the sound is directly in front of me, directly behind me, because I have the same delay and I have the same difference in intensity when they reach my ears, the same difference in level. It could even be straight above me or straight below me. Okay, so in this dimension, and if you can kind of, you know, extend cones like this, you'll see that I don't really, with these two sets of cues, I don't have enough information to tell that dimension. Is it up or down, forward or back, right? So I need additional cues, and that's essentially what these weird shapes are doing for us. So the ears are not symmetrical, you know, in themselves. They're not, you know, they're not something that equally reflects sound no matter where the sound comes from. They are designed so that sound from in front of us are reflected differently than sound from behind, above, or below us. So these unique shapes are really important for that differentiation of the origin of sound in this dimension, the Z dimension, I guess. You may notice, well, you know, these are shaped very much like they are funneling sound inward to the ear canal. That's true. But the interesting thing is there are really subtle differences in the way that certain frequencies would be reflected off these complex surfaces of the pinnae. Okay, or the head itself. Sound reflects off our head itself too. It's just not like funneled into the ear, you know, into the ear canal like what the pinnae does. So with basically living with these pinnae for our entire lives, as long as we haven't had, you know, injury or illness that has them go away for some reason, we become calibrated. So here's my term, calibrated to that specific shape in terms of how it reflects these sounds. And so if we start to, when we're children and we start to hear a bird chirping in the tree, and we have that experience go to both of our ears, and we see that's coming from that bird up there in the tree, we start to associate that frequency reflective pattern, that experience in the inner ear, with elevation. And so that sound came from over here, but also up, right? And it becomes subconscious. It becomes something we don't even think about. All right. So, but an interesting fact here is, if we have injury, and there are a number of cases of people like, soldiers, for example, that may lose a pinna due to some, injury or whatever, and they can get a prosthesis so that externally it's like, okay, you still have, this extension coming out of your head, but the hearing can change. So even if the hearing is not damaged, but the pinna is, replacing this very uniquely shaped and very well calibrated reflecting device with a different one can be very disruptive for people's perceptual processing, their auditory processing. So it'd be a period of recalibrating to a new pattern of reflections if you had to replace either of these. There are some really cool ways that we can play with the interaural time differences, interaural level differences, and then the frequency spectra that represent different sorts of elevations or reflected sounds. So we can record things with a head. So this is, basically I'm putting microphones in the ears right here, and these will naturally have sound absorbed through that head-like shape, and we'll get the interaural level and time differences at these two microphones. We'll even get some of the frequency spectra of bouncing off of something that's sort of like a pinna, right? So we call this a head-related transfer function. And if you have a sound file, you can essentially apply this transfer function or record it in a way where it's the transfer function is already embedded in it, where it makes it sound. If you can isolate the sound to the two ears, you can create a 3D audio experience that's very realistic. And we use this in some of our research. It's not going to work, for me to show you like in this lecture context. But if you have earbuds on, you can get an experience of, oh, it sounds like this thing is moving around behind me. And if you want an example here, this link right here is pretty great. Give it a try. It's not, I didn't make this. It's just something that I've used a lot of times as an example. Make sure you have headphones and it's a stereo connection though for it to work. It's pretty cool though. Give it a try. Okay. So just like with vision, we have cues about the auditory signal that help us to distinguish, is this coming from somewhere nearby or from further away? And this matters, obviously, because if we're localizing something, we can radially determine which direction it is, but we need additional ways to determine, well, now how far away is it? So we do know that the sound gets apparently less loud as it travels, and it follows the inverse square relationship. So if you double the distance, it's 1/4 the sound pressure level. Just like with illumination, it's a very similar relationship. If you double the distance, 6 decibels is the difference in sound pressure level. We worked that out in the previous lecture. But so if I go from one foot away, but it's doubled, 6 decibels. But if it's 1 foot away and it's really much more about the ratio of those decibels is much more meaningful. I'm sorry, the ratio of the distances is much more meaningful in the decibel difference. So this would be negligible. Now the spectral, just like with atmospheric perspective, remember, the further away we look, the bluer that light is and more fuzzy due to how much atmosphere that light has to pass through. Very similar for sound. And so just like with atmospheric perspective, where the blue light is the higher energy, and so it's more likely to pierce through and propagate further through the atmosphere, the low frequency sounds tend to have a higher energy and are less disrupted by propagation through atmosphere. So low frequency sounds travel further than high frequency sounds. And that's why you can hear this guy's bass when he is a mile away and coming down the road, but you can't hear the melody part of his song. The bass is going to travel. It's going to be much less affected by barriers in between the sound source and your ear. Yes, and then those sounds get muddier too, so to speak, because they're distorted, but those lower frequencies tend to persist, right? And so, yes, a good example, thunder. If you're close to a lightning strike, it's a sharp, high-pitched crack. The further away you are, the more it sounds like a low, drawn-out rumbling sound, and that's, again, the low-frequency parts of that sound wave are traveling further than the high-frequency ones. And finally, one of the key clues that we use for the depth or a sense the distance with a sound is the ratio of direct sound to reverberant sound. So for this person here, if she's in an auditorium, this guy's ear is going to receive, you know, that signal. The sound waves are going to reach his ears, but at slightly different timings because of all the different ways it can reflect around that space. So all those sound waves are getting to this guy's ears, but the fact that they're arriving at you know, with a distribution of times almost, is the clue that our brain uses to say, okay, that's not a whole bunch of people speaking at me really rapidly. It's one person making a sound and it's coming to my ears in a way that is perceived as that person is distant, or that sound source is distant from me. So as opposed to this guy talking right at me, I don't have all that reverberant sound that's coming back to my ears. So I might hear this sound source and this sound source with equal sort of loudness, but I can tell that this one's further away than this one because of how distributed in time the various parts of that sound wave are getting to me. All right, that's it for this section, this subsection. Thanks, everybody.